Hello, this is our narrated version of chapter 3, in case any video lessons don't work. Alright, so this is all about temperature. So we're looking at a weather map of sorts here, and you'll notice there's two temperatures for each city that they're showing. The high is, of course, the higher number on the left, and the low is on the right. And we might try to guess something about time of year for this. 50s in DC, Philly, and New York, so late fall, early spring, perhaps. So indeed, altitude is one of the basic controls of temperature. You'll notice here that these people are indeed mountain climbing. Well, that tent looks pretty neat, but the whole thing just looks terrifying to me. So in the mid-latitudes, which encompass really all the lower 48 states, we can have quite a wide swing in temperature variations throughout the year. Some places experiencing a variation on the order of a good 100 degrees. Okay, so this is old news. I think that Death Valley has, I could be wrong, but I'm pretty sure Death Valley has exceeded this record in the past 5 years. Anyway, these slides again go way back to a good 10 years ago. So the highest temperature ever recorded at that time in the Western Hemisphere was in Death Valley, and that was back in July 1913, and it was 134 degrees Fahrenheit. Pretty hot. So Mount Washington is in the White Mountains, which is in, I believe, Vermont. Well, it probably spans more than one state. Anyway, Mount Washington, it's only 62,088 feet tall, so it's more than a mile up, a good 1,000 feet more than a mile up. But, I mean, it's not the tallest mountain on the planet by any means, and yet Mount Washington is known as the home of the world's worst weather. So it is the highest peak in all of the White Mountains and in the entire Northeast. Anyway, they're just the way that they are situated, where they are, they're not terribly far from the coast, but it is a high peak. So they can get extreme cold, heavy snows, very high winds, icing events, and dense fog. And of course, they have a weather observatory up there. And in this image, the weather observatory is covered in a whole lot of ice and snow. Okay, so just some on this slide here, just some different ways in which we might keep track of temperature, like the high and the low, the mean or average temperature, the daily temperature range, annual mean temperature, and so forth. So, Hawaii. We do think of Hawaii as a tropical paradise, and certainly it is, but it's not necessarily all that hot. So its highest temperature, again going back about 10 years ago, was 100 degrees Fahrenheit, and it ties Alaska for the lowest high in the U.S. So isotherms. Isotherms are very useful on weather maps. Isotherms are lines that connect points of equal temperature. So if the lines are closer together, they indicate a steep temperature gradient and therefore faster wind speeds. And if the lines are far apart, that indicates a shallow temperature gradient and therefore lower wind speeds. Why do I bring up wind speeds? Because wind always travels from high pressure to low pressure, and temperature does affect air pressure. Okay, so isotherms here, again, so they're kind of like topographic lines for anybody that maybe has had the Earth Science Lab or just knows a little bit about reading a topo map. So the isotherms indicate the temperature distribution and temperature gradient. So every dark line here, so look over there at Myrtle Beach, it's 81. The line above it is 80. So everywhere along that line is 80 degrees. Anywhere above it should be lower, and anywhere below it should be higher. And in this little graphic here, Raleigh is right in between the 70 and 80. It's at 78 degrees. And then if you sort of color in those bands, that's what you see there on the lower left. Okay, what are the controls of temperature? Um, I know I mentioned in class, but maybe not yet on one of these narrated PowerPoints. My idea with these narrated PowerPoints is that you're going to sit down with some pen and paper or your tablet, and that you're going to actually take some notes on this stuff as if we had time to do this together in class. So controls of temperature, very important, definitely on your first exam. All right, so that star there is the most important and obvious. The receipt of incoming short wavelength solar radiation is the ultimate control of temperature. You know, where are you on the planet? How much radiation are you receiving? Now that's going to tie into control number 1. So we're going to go through, I guess, 7 different controls of temperature here. Latitude. So, of course, we already know that latitude matters, right? So the equator is at 0, the North and South Pole are each at 90. The Arctic Circle is 66.5 degrees north. The Antarctic Circle is 66.5 degrees south. By the way, the Arctic Circle is a frozen desert. Is it cold? Yes. Why do we refer to it as a desert? And you'll see images of the Arctic Circle and plenty of snow and ice. And you'll think, how is that a desert? And the answer is the amount of precipitation that falls is low enough it classifies as a desert. So not all deserts are full of sand. Number 2, differential heating of land versus water. We'll get into that more on a separate slide. We're going to see that water will heat up and cool down more slowly than land, and that makes a difference. Number 3, ocean currents play a part. We'll get more into that on a later slide. Number 4, altitude and elevation, of course. Yes, we have glaciers on the equator if they're up in the mountains. Number 5, geographic position. So are we on a windward coast or a leeward coast? But also, are we windward of a mountain range or leeward of a mountain range? And then there's cloud cover. Why does it matter? Because it reflects incoming solar radiation and helps to absorb terrestrial radiation coming back from the Earth. And then albedo, which is just a measure of reflectivity. So we're going to go through each of these in more detail. Okay, I do like doing these slides together in class, and we're going to aim for that, but who knows what's going to happen, and who knows how many people I'll have on quarantine, so I'm going to go through these slides in detail, even though we will do that in class together. It's more fun in class together. All right, so we are comparing Winnipeg, Canada, and San Antonio, Texas. And you're going from January to December, so you're going through the entire year with your summer months in the middle. So you'll notice that they each have a similar shape, but which city has a higher swing in temperatures throughout the year? Okay, that answer is Winnipeg. And why is that? Well, because it's at a higher latitude. They are both, well, Winnipeg is really in the middle of the continent, so its curve isn't going to be quite as flat as San Antonio. San Antonio is actually right near a body of water. Really, it's not too far from another body of water, so it's going to make a difference. All right, so what we're looking at here are just again reminding us that the most intense solar radiation you could get would be to receive the sun's rays at 90 degrees. Now, none of these are showing that, but we're basically just saying that, you know, the lower the angle of incident, or the more flat that angle of sunshine, it's going to be spread out over a further distance, and therefore it's just not as strong. Differential heating of land and water. Definitely write these things down when you are taking notes, because they are important for sure. Now, what's interesting here is that, golly. Okay, look at that image. So the inset on the bottom left shows you that you're looking at Southern California and the Pacific Ocean. So it's kind of hard to find the land in that larger image with the colors, but the land is in the darker colors that you see there, warmer than the surface temperature of the Pacific Ocean, which is shown there in the green. Okay, so land versus water. The differential heating of land and water is an important control of air temperatures. Why? Land heats up faster and more so to a greater degree, but faster than water bodies. Okay, the converse of that is also true. Land then cools down faster, as in it lets go of its heat faster, and tends to get colder than water bodies. So the flip side of that is true as well, as we mentioned in a previous slide, that water takes longer to absorb warmth, longer to heat up, but then it also holds on to it longer and it takes longer to cool. So maritime climates are mild. What does maritime mean? It means living on the coast, living close to a body of water like the Atlantic Ocean or the Pacific Ocean. Those climates are going to be more mild throughout the year and have less of a big swing in temperature throughout the year than continental climates. Continental climates like Winnipeg, Canada, in the middle of the continent, they will have a greater annual variation in temperature because they are far away from any maritime environment. So, here's just kind of a recap of some things that we have just said. So again, greater variation in temperature throughout the year on land than over water. Why is that? Well, you can pause here and read about this. Basically, there's a lot of mixing in the water, and so that's a big reason why the water takes longer to heat up, but then also takes longer to cool. And also the radiation coming from the sun can penetrate into the water column a lot better than it can penetrate into the land. Okay, question here. Then again, I hope to do in class. I don't know that we'll have time for everything. We'll do it all in this narration together as well. Okay, so 3 weather stations, all at 40 degrees north. So the same latitude as Pittsburgh and Philly. One is on the west coast, one is in the middle of the continent, and one is on the east coast. Okay, so, and you may not necessarily know the fully correct answers yet because we have not talked about windward versus leeward coast, but we're going to do that now. A, which one of these stations is going to have the hottest summer? That one's actually easy, the one in the middle, okay, because they're not near either body of water. They are not anywhere near a maritime environment, so the station in the middle will have the hottest summer. Which one has the coldest winter? That will also be the station in the middle, because they have a greater swing in temperature throughout the year. Okay, and then which one has the lowest annual range of temperature and which one has the highest? And we'll throw in another question, which one's in the middle? Okay, so the highest annual range of temperature is clearly the station in the middle. But then we have one on each coast, east coast and west coast. What's the difference here? The west coast is a windward coast, meaning that the United States, in the middle latitudes here, we are in a band of winds known as westerlies, meaning that the winds blow from west to east. Winds are always named for the direction from which they blow. Westerlies. So the west coast is getting air blown in from the west, bringing all that moisture and warmth from the Pacific Ocean. The east coast is still a maritime environment, but they are a leeward coast, meaning that the winds are going to blow offshore. So they're not going to have quite as enhanced a maritime effect. So the west coast will have the lowest swing in temperatures throughout the year. The middle will have the highest swing in temperatures throughout the year, and the east coast will be in between. And then here are some answers, because this PowerPoint is also specifically created for the online version of this class. Nothing wrong with that. Nothing wrong with a little overkill on our information. Always better more information than not enough. Okay, I really like this image here. We are looking at Vancouver, Canada and Winnipeg, Canada, both in Canada. Looking at their locations, as far as latitude goes, they are at the same latitude. So that's not a factor here. So we're going to compare Vancouver, their annual temperature swing is in the red line. Winnipeg, the annual temperature swing is in the blue line. Okay, so who has a colder winter? Winnipeg. For sure, we would guess that right away. But who has a hotter summer is actually Winnipeg. Okay, so, and then you'll notice that the curve for Vancouver is more flat than the curve for Winnipeg. All this is because Vancouver is in a maritime environment. They are on a coast, a windward coast, so a much smaller annual temperature range. owing to the strong marine influence of the Pacific Ocean. Personally, I would never live in Winnipeg, although I do like Canada. I'd live in Vancouver. Okay, so here's another look at geographic position. Here we are simply going to compare Eureka, California to New York City, and we're not going to have any weather station in the middle to cloud things up. So who has the coldest winters? New York City, of course. Everybody knows New York City can have some cold winters. But who has the hottest summer? Well, New York City. Okay, so notice there's a lot more swing in the temperature curve for New York than Eureka. Eureka is pretty flat. In other words, their temperature doesn't vary that much throughout the year. Why? They're on a windward coast. They're getting the full moderating effects of a maritime environment. I would probably like to live in Eureka, California, if I could afford to buy a house, which will probably never happen. Okay, so Seattle, Washington versus Spokane, Washington. Okay, again, both of these cities appear to be at pretty much the same latitude. Okay, so what's going on here? I want to point out that bumpy feature that goes kind of north and south that's sitting in between Seattle and Spokane, Washington. Those are the Cascade Mountains. They're there because we have a subduction zone, plate boundary, offshore. And you are thickening the crust, building mountains, and some of them are volcanic. Anyway, so what's going on here? Seattle is right there on the windward coast. They're getting the full moderating effects of a maritime environment. And Spokane is cut off from the maritime environment. Okay, and not just by distance, but they're really cut off from that maritime environment because of the mountain range. So Spokane is on the leeward side of that mountain range. So Spokane has colder winters and hotter summers than Seattle. Seattle has a flatter curve because they are on the windward coast. So the north and southern hemispheres are very different from each other, and this is a great way to compare them. I really like this graphic. It's pretty awesome. It shows that, yeah, so the northern hemisphere is the land hemisphere, and the southern hemisphere is the water hemisphere. So there's more temperature variation throughout the year over land than water. Therefore, more continental material in the northern hemisphere. There's just in general more temperature variation throughout the year in the northern hemisphere than in the southern hemisphere. I do not like these images here. You are free to pause this and read through them. I especially don't like the graph over on the right. Ocean currents. Well, this is fun stuff, and I do plan to cover this for the in-class portion. But again, I need to prepare these for people that can't come to class, or for summers as well when we never have class. So let's just get started. Okay, I'm going to point your attention to the North Atlantic Gyre. You see the Gulf Stream there, very famous surface water current, and of course it's warm. You see that because the arrow is red. So the Gulf Stream, they just give it a different name there in England. They call it the North Atlantic Drift. It's the same current. And then notice that south of London, it heads back south, and it has been cooling. So now it's the Canary Current, and it's colder. It's blue. So the North Atlantic Gyre has these surface currents that are moving in a clockwise fashion. Now, it's always true to say the following. Now look at North America, the continent, all right? North America, the continent. Notice that on the east coast, you have a warm water current, but then go over to California on the west coast, you have a cold water current. Okay, now back to the North Atlantic Gyre. What does this mean? It means that when you're looking at these gyres, be it north or south hemisphere, that on the western edge of the gyre you have warm water, and on the eastern edge of the gyre you have cold water. So North America sits between two gyres. It sits between the North Atlantic Gyre and the North Pacific Gyre. So that's why you might often see images of surfers in California, even in summer, wearing a wetsuit. You think, gosh, isn't it warm in LA this time of year? Sure, the air is, but not the water necessarily. Something else to point out is that the North Atlantic drift is very important to Western Europe. Okay, and it gives them a more moderate climate than they would otherwise have just based on latitude alone. Okay, so we would never want for the Gulf Stream and North Atlantic drift to ever shut off. That would be bad for Western Europe. Anything else we want to point out? I'm going to point out the North Pacific Gyre. So look over on the left of the screen, and you guys, I'm sure have already heard this, but these gyres, in particular the North Pacific Gyre, is especially bad for this. They tend to collect a lot of garbage that has washed off of ships or been thrown off of ships or thrown off the beach or washed off the beaches in tsunamis. And this garbage and floating plastic just kind of hangs out in that gyre, just swirling. Yeah, I guess until humans get their act together and go clean it up. All right, so let's take a look at what's written down there at the bottom. Important stuff here. So poleward moving currents, meaning currents moving towards the poles, carry warm water with them. And then equatorward moving currents, meaning they are coming from the poles moving towards the equators, are bringing cold water with them. This is neat. This is a satellite image showing sea surface temperatures off the east coast of the US in April back in 2005. So the lighter colors are warmer sea surface temperatures as far as Celsius goes. So you see the Gulf Stream, and these eddies can form in the Gulf Stream because, as I'm learning in my grad class at NC State, because of turbulent flow. Anyway, so you definitely see a clear temperature signature here of the Gulf Stream. Now, way back in Ben Franklin's time, which would be 1700s, I believe, we had already discovered the Gulf Stream. You know, and I might guess that we had discovered it more as a speed thing at first than a temperature difference. So the Gulf Stream travels fast, and if you are trying to take your sailing ship from the East Coast of the United States over to London, you know, it might behoove you to be in the Gulf Stream and get a little bit of a boost there. Anyway, we knew about it as evidenced by this woodcut image of the Gulf Stream made by Ben Franklin. Okay, so this one's kind of neat. So this is going to emphasize something we discussed earlier for North America, but now we'll look at it for South America. So we'll compare Rio de Janeiro, party town in South America, to Arica in Peru, or on the west coast, assuming it's Peru. All right, so what do we see here? We see that on the east coast of South America, you have that warm water current as you would expect, just as we have on the east coast of North America, the Gulf Stream. This time it's called Brazil Current. And on the west coast of South America, you have a cold water current, just as you would have on the west coast of North America. You have the California current, but here it's the Peru current. So, does this matter in the overall climate of these areas? And the answer is yes. Okay, so we are looking at the average annual temperature swings comparing these two places. Rio is warmer than Arica. Now they both have about the same shape, and there's not a whole lot of dip to this curve. It's somewhat flat, relatively flat. Why? They're not far from the equator. Okay, altitude. In the troposphere, of course, we expect temperatures to decrease with altitude. And of course, the atmosphere is thinner at higher altitudes, meaning you don't have quite as many air molecules. So higher altitudes tend to produce a greater daily temperature range. Sorry about that. Images, just to show us what do these cities look like. You got Quito, and then you got Guayaquil. Where would you rather live? I'm thinking Guayaquil looks kind of cool as for a place to live, and you could always just visit Quito. In the summer, would you want to break from the temperature. Okay, so what we're looking at here, another example from South America, Concepcion versus La Paz. So La Paz is up in the Andes Mountains. Concepcion is on the leeward side of those mountains. Basically, we're looking here at an altitude difference, even though I don't have the exact average altitude of these two cities written down. Other than that, the curves look relatively similar, just that there's a big difference in your average annual temperature throughout the year. And again, neither of them have a huge swing throughout the year. Well, they're not that far from the equator. So what about cloud cover? How does it affect temperature? Cloud cover basically brings down the temperature range of the day. Your high will be not as high and your low will be not as low if you have thick cloud cover. Why? So the cloud cover will reflect some of that incoming solar radiation, but it will also trap some of that outgoing terrestrial re-radiation leaving the Earth. All right, so this is basically what we just said in the last slide, but explained maybe in a little bit better detail. So imagine that you have clouds, all throughout the day and the evening. Yes, you're going to have a reduced daily temperature range. So a question down there at the bottom. So think about nighttime, maybe November, camping in the mountains of North Carolina. Okay, so what night will be colder, a clear night or a cloudy night? Clear nights are always colder. Cloudy nights are always warmer. Why? Because the presence of clouds helps to trap that terrestrial re-radiation. A clear night, that terrestrial re-radiation is just going to emanate outwards. Yeah, clear nights are always colder, but you can see the stars. So cloudy days flatten the thermograph curve. So this curve is not through the entire year, but just one day, one 24-hour period. So you're comparing here a clear day in red and an overcast day in blue, and you just see that your curve is flatter. Your high is not as high and your low is not as low. I have to admit, in the summers, boy, I love an overcast day. Absolutely. Of course, I like them in the winter as well, because I'm a skin cancer survivor. So boy, clouds are my new best friend. Okay, so this is Myanmar. This is not far from India. This is on the Indian Ocean, where you see a little map there in the inset. So what we're looking at, well, we're looking at a couple things. We're looking at, okay, so the red line across is the average temperature throughout the year, but then the green bars are showing you when you have rain in centimeters and inches. Okay, so you may have heard of the Indian monsoon seasons. Myanmar experiences these as well. We'll talk about them more in a later chapter. It has to do with the differential heating of land and water. So in the summertime, the continent is warmer than the ocean, so you get lower pressure over the continent, and the winds blow from the ocean to the land, bringing you a lot of rain, as you see there in the green bars. More rain in the warm months. And then in the wintertime, all that switches, and the continent is colder than the water. The water holds on to heat. So your winds then switch to blowing offshore, so you have a lot less rain. Okay, so the highest mean temperature occurs in April, just before the onset of heavy summer rains. Abundant cloud cover associated with the rainy period reflects back into space the solar energy that would otherwise strike the ground and raise summer temperatures. So their summer isn't necessarily all that hot. It's not necessarily the hottest time of the year because of all the cloud cover they get. And as you might guess, they're not terribly far from the equator. Look how flat that red curve is. So looking here at Barrow, Alaska. Gosh, how many of you would live there? Raise your hand. I'm not raising my hand, although I wouldn't mind to live in New England or the Pacific Northwest or Northern California. Here we have ice and snow-covered surfaces have higher albedos, meaning higher reflectivity. So the more snow and ice cover you have, the more you reflect incoming solar radiation. So you end up keeping air temperatures lower. Here we go. In the wintertime, you might see some hint of the Gulf Stream there in the 50-degree and 60-degree lines, isotherms, the 50 and 60-degree isotherms, they're leaving the east coast of the U.S. And then you see signature of the North Atlantic Drift as that heads on over to Western Europe and then starts to head south. So we do kind of see some signature of the ocean current. And now we have moved back to the summer image, and now I want you to look at the west coast, and you see the 60 and 70-degree lines bending downwards. Where you pick up maybe the signature here of the California current, and that's in the summer. Yeah, so basically, let's compare, say, Southern California water temperature to North Carolina water temperature. And the North Carolina water temperature will be in the 70s to 80s, whereas on the West Coast it's going to be 60s to 70s. So again, they might wear a wetsuit to surf even in the summer. And then these are the answers that we already talked about. But you can pause the slide here and look at those in more detail. Again, more answers here in more detail. Okay, annual ranges are small near the equator and increase towards the poles. Yeah, so what we're looking at here, these isotherms are annual ranges, not a temperature for that day or whatever, and not even an average temperature, but a range. So I want to call your attention to the top part of North America there where it says 90 degrees Fahrenheit. That's your average range throughout the year, 90 degrees. Wow, that's a big swing. And then I want to point you to, say, near the equator, your average temperature range might only be 5 degrees Fahrenheit. Imagine your temperature throughout the year only varying by 5 degrees. You better like where you live, and you better like that temperature, because you're not going to get any variation. You're not really going to have seasons, and you better like the clothing that corresponds to that temperature. I couldn't live in that kind of place. I know. I got to put on a hoodie and a sweater eventually, and some jeans. Anyway. Looking forward to fall and winter. Now, look over in Siberia, okay, so northern Russia, over there in Europe. You actually have a annual temperature range there. The highest on the planet is 110 degrees Fahrenheit. Okay, so that answers that question at the bottom, which region has the highest range? And just in general, the Eurasian continent has the highest range. It is not only the biggest continent, well, yeah, it's just the biggest continent. We'll leave that. So, all right. Bottom line, annual ranges are small near the equator, increase towards the poles. Outside of the tropics, annual temperature ranges increase as we move away from the ocean towards the interior of continental land masses. This is a thermograph of a 7-day span in Peoria, Illinois. So a thermograph just is a continuous, never-ending display of the temperature changes, from minute to minute. This one goes over 1 week. This is back in May of 1992. All right, so typical daily rhythm, minimums around sunrise, maximums mid to late afternoon. Yeah, anyway, kind of neat. Maybe pause this and take a look at that. All right, so, and then down there at the bottom, something that we will discuss in class if we have time, and I will want you to know for your first exam. When do we reach the overnight low temperature? It's shortly before sunrise, when we've had the maximum number of dark hours for the Earth to be releasing all of its heat. Okay, and then when do we reach the high temperature of the day? Everybody knows that. Afternoon, maybe around 3-ish. It can vary from time to time, but it's going to be mid to late afternoon. Why is that? Because there is some lag time between the incoming solar radiation that begins when the sun comes up and the terrestrial re-radiation being spit back out from the Earth and trapped by greenhouse gases. Okay, so minimum daily temperatures, again, usually occurring near sunrise, causing early morning fog in your warmer months or frost in the winter. I can't remember the last time I saw frost in Pembroke or even Southern Pines where I live. Oh well, I miss winter. So this is kind of cool. What you're looking at there on that graph on the top is it's a 12-hour period, and it's showing in yellow the incoming short wavelength solar radiation, always shown in yellow, and then in red it's showing the Earth's terrestrial re-radiation, or the outgoing radiation at a longer wavelength, infrared, always shown at red. Okay, so you have this time that you have there in the yellow peak, more radiation received than lost, spanning less than 12 hours, and then you have all that time in the red on either side of the graph that you're actually losing more radiation than you receive. And then the graph in the bottom, again, this 24-hour period here, showing you roughly about when the minimum temperature might occur and the maximum temperature might occur. All right, so we have a surplus and a deficit. Are they listed on there? Well, the surplus is in the yellow peak and the deficit is in the red. That's on the top graph. All right, so certainly you can pause this and read that in more detail. We're going to go through some slides quickly because they're all about thermometers, and we're just not going to spend a lot of time on thermometers. By the way, thermometers no longer use mercury. When I was a kid, a few decades ago, thermometers, like to take your temperature if you were sick and you went to the school nurse, those thermometers actually had mercury in them. And I know that because I think I accidentally broke it once at the school nurse, like it fell out of my mouth because I was that sick. Anyway, and it broke and there was mercury on the floor, and I thought it was the neatest looking thing ever. And of course the nurse is like all flipping out, and we got to clean it up carefully because mercury is poisonous. That's why you may have ever heard the phrase mad as a hatter. People that made hats, they used mercury in making hats decades ago, and they tended to go crazy. So nowadays it's alcohol. Of course, they're showing here the mercury alcohol versus the, the mercury thermometer versus the alcohol thermometer. This is a thermograph, which will just kind of like a seismograph, will show a continuous, over hours and days, a continuous record of temperature changes. This is a typical instrument shelter to put your weather instruments in. White for high albedo, meaning high reflectivity like snow. Louvered or slats in it for ventilation. You want to have it at least 1.5 meters above ground, not right by buildings, not in shade. Okay, so this is a modern instrument shelter containing an electrical thermometer called a thermistor. Very accurate. Here they are explaining the differences between Fahrenheit, Celsius, and Kelvin. And then you have the conversions over there on the right. Now, I think there's an app available that you can, you can download on your phone and then just type in the temperature in one of those Fahrenheit and figure it out in Celsius and vice versa. Back to where we were. Many years ago when I was working on my first undergraduate degree, which was business and economics, I was a bartender and I wanted to go to law school. And some of my bar guests were lawyers, and so I would sometimes pick their brains over, what's a good law school, what kind of LSAT score do I need, how much debt will I incur. And I was talking to one of my lawyer friends, and I brought up this hot coffee thing, and he explained it to me. And they've now made a documentary of it, and I think it's called Hot Coffee, and I recommend watching that documentary if you can find it on Netflix. You don't have to be wanting to go to law school to watch it. You should just watch it. Anyway, here was the problem. So McDonald's was keeping their coffee way hotter than it should have been to try and make it last longer so that they could serve old coffee and people wouldn't notice. So it was definitely a good bit above 100 degrees. And it was an elderly lady that went through the drive-thru. Somebody else was driving her, and I think she was wearing a skirt or a dress, and the person driving handed her her coffee, and the lid wasn't on it all that well. And of course, it was an employee that had done that. And as she tried to drive away, this coffee spilled on the woman's legs. Okay, so she suffered third-degree burns on her legs because the coffee was hotter than it should have been. And in that documentary, they show pictures of her legs, and it looked like a shark had taken a bite out of each one of her thighs. I'm not kidding. That's how horrible it looked. So at the time that went around, of course, you know, people that think lawsuits are frivolous thought it was stupid. Well, all coffee's hot. She should have known better. But you know what? It was a valid lawsuit, and she did end up winning some money, as she should have. Because the point of the lawsuit was to punish McDonald's and make them finally do the right thing and not have their coffee so darn hot. The urban heat island effect. We're almost done with this. That's great because it's about time to go meet my friends for a beer. And the Maine lobster truck is going to be at the Southern Pines Brewery. Anyway, urban heat island is a real thing, and here they're showing a picture different than DC. I have been to DC, and I don't think any part of DC looks like that picture on the top. Maybe that's New York or Dallas or Chicago. But the map on the bottom is DC, and they're showing there in the different colors and the isotherms, they're showing the temperature. Now this is, I'm going to ask you guys, looking at those isotherms, what season must this be? Everybody see that it's like negative 2.2 degrees Celsius? Okay, it's winter. That's below freezing. So it's wintertime and the temperatures are cold, but you see there that in DC the temperatures are warmer. Okay, so why the urban heat island effect? Dark pavement, of which we have a lot of, you know, in our cities, absorbs solar radiation. So you're absorbing more solar radiation than the countryside, automobile engines and exhaust, leading to more heat, heating and cooling of buildings, leading to more heat, lots of people walking around, leading to more heat. And then, so maybe that's Philadelphia in the picture, because now if we look at the table in the top left, average temperatures in Celsius for Philadelphia, airport versus downtown. Airport is on the outskirts of town. So you might pause this and look at that. And then here are satellite images showing the urban heat island of Atlanta, Georgia back in September 2000. So the image on top is showing you where do you have city, everything that looks gray, landscaping, concrete, and then everything that looks green, of course, is away from the city where you do have some green space. And then the image on the bottom, the red, shows you the warmer colors. And, you know, that, boy, those images match up very well. Where you have the cities and a bunch of pavement and concrete, you've got a warmer temperature than the surrounding countryside. Here is just a hypothetical showing, you know, the urban heat island effect. We're going to skip this. Okay, so we skipped everything about degree heating days. Dr. Edgell likes to talk about that. It does have something to do with agriculture. You guys can read about this in your textbook or, you know, on the internet, at the NOAA website maybe, National Weather Service website. So we're going to skip it. You could also pause on the slides and read through it. Okay, so wind direction influences temperature. Northern hemisphere. Winds coming from the north are bringing cool temperatures from the north. Winds from the south are bringing warmer temperatures from the south. Heat stress and wind chill. Okay, I think this is our last topic. All right, so apparent temperature is the temperature a person perceives, feels like. Okay, so everybody, you know, we talk about the heat index. Okay, so the heat index works like this. My ambient temperature today is 90 degrees. Okay, but if you have a high humidity, that's going to add to that. So they might say your heat index today is 95. The ambient air temperature is 90, but because the humidity is 80%, it's going to feel like 95. Therefore, the heat index is 95. Okay, so heat stress is caused by high temperature and high humidity, as in your body sweats, but if the air around it cannot evaporate it, it's too hot and the air is saturated, well then your sweating isn't bothering to cool your body. And if you don't get to cooler temperatures quickly, it can lead to heat stroke and death. So you might pause here and look at this chart. It's very interesting. It's basically the heat index chart. So air temperature on the left and relative humidity, and then what it'll make you feel like. So let's say that the air temperature is 90 degrees, but your humidity is 80%. Wow, they're saying that your heat index would actually be 113. So ignore the example I just kind of pulled out of the air earlier. I was kind of way off the mark. Okay. Yeah, or in other words, if your mean air temperature is 80 degrees and your your humidity is 85%, it'll feel like 86. Look in the top left corner there. So if you are in Arizona and your high temperature of the day is 110, and it's that time of year when you get moist air moving in from the Gulf of Mexico, and your humidity, it was 40, your heat index would be 136. Anyway, and then in the colors there, you see yellow, caution, fatigue possible, light orange, sunstroke possible, extreme caution, danger in the mid-orange, and then extreme danger, heat stroke likely in the red. And then on the opposite wind chill, which, yeah, I don't really think about the wind chill anymore living here in North Carolina. I just don't. Anyway, this does happen in the winter, and it is a thing everywhere. But you really notice it, as you move to further north. Chicago, windy city and pretty high latitude and in the middle of the continent. Wind chill is the cooling power of moving air. So it's going to evaporate moisture from your skin, and it's going to cool your core body temperature and makes you feel colder. There's a new wind chill chart, I guess, on the next slide. Yep. So something we don't worry about quite so much here, but boy, you go moving further north. Some of you might be from the north. You might be more familiar with this. Anyway, so we'll just look at a couple of things. And of course, they have in colors the time it would take for exposed parts of your body, like your nose, to become frostbitten. Wow. Anyway, so if your temperature is 10 degrees Celsius, but your wind speed is 55 miles an hour, then it's only going to take 30 minutes for your nose to become frostbitten. Anyway, I need to go ahead and cut this off, so you can pause here and look at the slide on your own if you would. And of course, yeah, so heat waves can be quite deadly, and they can kill dozens of people. Yeah. And back in 2003, there was a very deadly heat wave that hit Europe. Milankovitch cycles. Gosh, we're so close to being done. We briefly mentioned these in class. They are a lot of fun, so this will be our last topic. This is going to take forever to save. Okay, precession. The Earth's poles wobble over time. Pull of the sun and the moon. It takes 25,800 years to complete. So currently our North Star is Polaris, but 12,900 years from now we'll swing around 180 degrees and our North Star will be Vega. So what does this mean? It means currently perihelion, when the Earth is close to the sun, is in the winter, and aphelion, currently, when the Earth is furthest away, is in our summer. So currently, the northern hemisphere has slightly milder seasons than the southern hemisphere. But 12,900 years from now, that's going to be the opposite because of changes in precession. The Milankovitch cycles, by the way, are the long-run controls on ice ages. And of course, plate movement is a control on that as well. How about eccentricity of orbit, which just means shape of orbits? It's always an ellipse. It's never a perfect circle. It could be more or less elliptical due to the gravitational pull of Jupiter mostly, but also Venus. Cycles are on well, there's 3 different sets of cycles on the order of tens of thousands of years. Okay, so when the orbit is more elliptical, perihelion is closer to the sun and aphelion is further than when it's more circular. So this helps to allow for ice ages and warming periods. And then even the degree of tilt of Earth's axis in the long run is not fixed. In the short run, it's fixed, and I tell you that in class. Right now, it's 23.44 degrees, and we point in the same direction as we move around the sun in the course of a year. Okay, but this tilt varies between 21.4 and 24.5 degrees. Okay, so this cycle varies on the order of 41,000 years, and it affects the difference in severity between winter and summer in each hemisphere. Here is a great graphic showing all three aspects of the Milankovitch cycle together. What causes these? According to Neil deGrasse Tyson, one of my favorite physicists ever, on his show Cosmos, which is a remake of the Cosmos from the 70s with Carl Sagan, variations in orbit, axial tilt, and wobble are caused by gravitational pull of Venus and Jupiter. Jupiter is bigger and exerts more of a pull. What about Mars? I don't